Alright, welcome back and let's continue working on Kroof. So last time we added an interactive shell for our language, for the interpreter, and since then I did some more off-screen work and I added a few dependencies, console and dialog gear, which make the shell a bit prettier, although they don't add extra functionality. It's just like a different way of using it, and it still works the same. So we just type in Kroof code in the interpreter, like eval 1+1, and then we do a dot to indicate that it's done and it can move on, or like run the parser and type checking on our evaluation. And then we can type begin to start working on the expression, and then we'll see like an input selection menu. This is provided by dialog gear, I guess, and here you can just go and choose one of them. So for instance, we choose to evaluate 1+1, and then if you type in next, it's gonna ask you which implication you want to use for the current selected evaluation or theorem, right? And for instance, here you can choose this one, which is the built-in one that converts from a number to successor based like pattern matching. So yeah, and then it's gonna ask you where you want to apply it. You want to apply it for the first term or the second term. We hit OK. Then you can also use show to show you the current steps that you are making on the expression so far. So we applied this formula and we get from here to here. And yeah, it's basically the same as we did with the automatic solver, but it's doing it manually, which I think in some cases it might be better because you might have a really complicated thing and you want to solve it manually because the solver is trash and it's I mean, besides 1+1 and 2+2, it's kind of bad. I mean, we have a few examples with what it can do, like automatically, like even Fibonacci numbers. But if you go beyond 4, it's kind of slow. And maybe one way to try and improve this is by implementing caching, which I kind of want to do it today. And yeah, but let's not go into that yet. So we have this this step so far, right? We also have a help command to show you all the possible options, and yeah, even backtracking. So if you, let's say, do next and you choose something that you don't like, for instance, let's say a is equal to a+0, and we do something like this, you're like, oh what the fuck, I have to go back because I don't like this. This leads me to something that's not the right solution. So you can just type back, it's gonna do a backtrack and it goes back to the previous step, and then you can continue with next. Let's choose a is equal to, or I guess we can apply shift like this, so it gives us 0 plus successor 1. Then we can apply next again. We have 0 plus a is equal to a, successor 1, and then we apply this one, which gives us 2. And once you get to the result that you are happy with, you hit end, and it's gonna say that it was completed. Although now if I hit begin again, I'm gonna see the evaluation still here, which is something that I would like to maybe convert this thing into 1+1 is equal to 2 or something, like add some caching, which I think would be kind of interesting. So yeah, and other things that you can do is, for instance, proof, well, I guess I wanted to clear the screen, but yeah, we cannot do that because we don't have read line wrap. Okay, anyway, so proof for all a in n, for all b in n, We can even do things like a plus b squared is equal to a squared plus 2 times a plus b plus b squared. So we can try and prove this formula. Now, I guess some parsing error. What? Let me just move it here and maybe it's a different keyword and I forgot about it. Let me just check in the tokens. So it's proof, as in so in the Lexer we have, I guess it's proof, yeah, whatever. So let's just okay, so let me just copy paste this thing. I'm gonna type it here just so I can copy paste it. So if we run this thing, we can do proof, right? And if we hit begin, we are gonna see it as a theorem, right? And the thing is, at this point, because I tried this this formula to do it, it took something like 45 steps, which is like pretty long. So I don't think I want to do it like right now. Although maybe it's interesting to see how we can prove this thing actually. So maybe we can do it. But what I would like to do is to try and add some caching so we can maybe prove certain like smaller things. Like for instance, we can prove a times a is a squared, and that's gonna help us. Maybe we can prove even other things like smaller steps and then apply those steps on this thing. So I think that that could be pretty helpful. And how that would work maybe is, let's say we have this thing. We also say proof that for all a in n, a squared is equal to a times a, and then we can actually prove this thing, right? Like type in next, obviously. We convert the two into something like this because we have a formula for this operation. Then we can apply this one, like a to the power of a successor of a number is a to that number multiplied with a. That's basically the formula that we have. Okay, and then a to the power of 1 is a, obviously, and then we can try to do and it's gonna say the theorem has not been proven yet because you know, left hand side is not equal to right hand side, so you can also test if you are right like this by typing and it doesn't work. So if we hit show, we can see that we are still working on this theorem, and yeah, like a squared is a times a. We got to this step, so we can apply parentheses of a is a. We get to this, and then we can just do and then it's going to say the theorem has been completed. Now if we type begin, we are going to see that this theorem is proven, right? But it's still not available as an implication. So that's what I want to do today. Basically make this thing available as an implication so that we can use it here. Like if I would try to prove this one and type in next, I want to see it in this list here because we have something squared, which yeah, we can use this entire thing for this one. So I think that's what I'm trying to do today. All right, so let's go ahead into the solver, and we have the interactive solver. with a bunch of comments. So I guess this should be pretty easy though. So how this entire shell works, I guess maybe it's interesting to see also another example. Like, let's say we have a val 1 is smaller than 2. Oh, because I don't, I have to include something different. stdlib crew. A val 1 is smaller than 2. So in this one, right, if we are trying to evaluate it, if we hit next, we have this this theorem which says that a less than b is equal to true if b is greater than a. I know it's kind of weird, but we have this as a relation, and the less than is an operator. So yeah, it's kind of annoying, but it's just more for the example. So if we try to use this one, it's gonna say it's true, but we have this where condition, right? So we hit it and it's gonna say the evaluation requires proof of this, right? And if we try to hit end, it's gonna say, okay, you cannot end it, you have to prove this thing first. If we hit show, it's gonna say, okay, we have this thing, but we need again to evaluate this. So we have to hit begin, try to prove the theorem. It's gonna be true because it's just gonna compare the two numbers. So it's gonna say, okay, that's fine. And now if we hit show, it's gonna say, okay, this is gonna be true, and it requires proof of this, which is proven. And now we can actually hit end, and it's gonna say, okay, that's good now. So it works in a stack-based approach, because we are gonna have an expression, and then we might have some conditions that need to be proven. Those are gonna go on top of the stack, and you have to prove them first before you can continue working on your whatever evaluation you were doing. So it's gonna be on a stack, which I think it's kind of a cool concept. Kind of a shame I didn't do it on a video, because it was quite interesting. But just to keep it in mind, it's working like a stack. I mean, as in programming languages, you have stacks, like a stack for function calls. It's kind of the same thing. You have to complete the theorems before you can return from them, basically, right? And then we have a hash set with the proven theorems, and I guess the stack for our things, and then the proof stack is what you need to prove. Okay, and the idea is, I guess, once we add an item to the proven hash set, we might want to add it also to the implication list. So I think that's what I want to do. So let's try to go to the read end theorem, and here somewhere we are gonna add the thing to the proven list or hash set. So I think I want to add the original theorem as an implication. So self.implications.push, and let's add it. I think this should be enough, actually, to be honest. So yeah, I think that should be enough. Maybe we can also in read end evaluation. So if you are evaluating something, we could build a theorem out of it, or an implication out of this thing. What do you think about that? So how can we do that? We have the original expression, so the expression that you started with, and at the end of this thing we are gonna have the result, so evaluation expression. That's the result. And inside of the evaluation we also have the conditions, so we can use the conditions as the preconditions for the implication. So let's try to add that. So we are gonna do something like, where is, yeah, this one. Okay, so here, let's say we do it here. Although, just to be consistent with this other function, let's do it after we find the original thingy. So here we are doing something like original conditions, or I guess original is just an expression. So let's do evaluation.conditions to get the conditions, and here we need to put a relationship, I think, right? No, it's a vec statement. Okay, so here is going to be a vec for the conclusions. So let's have something like let conclusion is a vec, and it's going to have a relation. No, really, I don't have that. Okay, I guess it's statement. No. Wait, what? Statement. Okay, let's do it like this. Statement node dot relation node equality. Okay, I guess it's new, and this is gonna, oh, what's a relation now? What the fuck? Relation kind, token, left and right. Okay, fair enough. So it wants the kind. Let's do relation kind equality. For the token, I'm not sure. Token kind, and here we are gonna give it token kind equal, I guess. Then for the left hand side we are gonna use original expression, and for the conclusion we are gonna have evaluation dot expression. Right, and that's gonna be our kind of conclusion. We just need to make a vec out of it. So vec conclusion. Okay, I assume we need to clone each thing here. And we have the original theorem. And we can just push it in the implications. So if we do something like 1 plus 1 is equal to 2, then we can reuse 1 plus 1 is equal to 2, basically. Right, so let's try to run it again and see if evaluations work. So eval 1 plus 1, we begin, next. I mean, we did 1 plus 1 so many times, we are already experts at 1 plus 1. Okay, let's do next, 0 plus a. Okay, and if we end it and we try to evaluate, let's say 0 plus 1 plus 1, just to have something different, and we try to begin this thing, if we hit next, we should have 1 plus 1 is equal to 2, which is kind of cool. And then we can apply this one, and then this one, and then we end. And yeah, sure, for evaluations you can hit end anytime, but yeah, you know, it's up to you when you want to end an evaluation. That's what I was thinking. Okay, so this should work for evaluations. That's kind of cool. The only thing that maybe it's missing is saying here what the value is. So can we add that as a feature? Wow, there's so much code, Jesus. So we have something like evaluations in here. Maybe I want evaluation solutions or something, like solutions, and it's gonna be a vec option expression node, because the solution is gonna be an expression, right? That's what I think. So we're gonna have solutions. You know, it's kind of like a mess, the code, but I'm like, who cares, right? It is what it is. So here in read begin, for theorems we are showing something like proven. For this thing we are not. So let's do that. So here we are iterating evaluations. Let's do zip, and let's add self.solutions.iter. Here we are gonna have evaluation and solution, right? The optional expression, and I guess that if let some solution is equal to solution, we are gonna print eval is equal to solution, else it's just the evaluation. All right, I mean, whatever. If it works, it works, to be honest. Let's run it again. Let's do eval. Let's do 0 plus 1, honestly. So here, okay, fair enough. So solution is empty. Solutions is empty, right? So when we are doing the new thing, we should, or I guess when we are adding a new evaluation, we should also add the solution for it, which, you know, empty. Oh, and I mean, it's, yeah. Okay, let's go ahead and see where this thing is. So here, for, can we have something like solutions extend? I know I have like once, iter once. Do we have something like similar to once but many times? repeat n, and we are gonna do none program evaluations dot len. So we're gonna do something like this. We extend that. Right, so we can add nones. Perfect. For each evaluation, we're gonna have a none. And the next thing is when we do read and evaluation, we should modify the solution. So here we have evaluation expression. But it's interesting, how do we know? Maybe it should be a hash map. Yeah, maybe it should be a hash map. Because the evaluation node is like, we have to search for it. Okay, let's make it a hash map. Solution. Let's go here and let's make it hash map from evaluation node to expression node, right? So this is gonna hold the solutions for hash mapping for the evaluations. So here we cannot really zip with it. I don't know, something like this. If let's self.solutions dot can I get an item? Look, fine. Really, I cannot. Why don't I have I was okay, yeah, fair enough. Okay, let's leave it like this for a second. Self.solutions. Okay, so there we don't have to do anything. Here I might want to, but why does it? Does it want something with? Okay, evaluation node doesn't have a hash on it. This one has, so this one also needs hash. Okay. So we have to insert basically original is the expression. So original is just the expression. I mean, evaluation node new, it wants the conditions and the expression. Okay, fair enough. So evaluation dot conditions dot clone, and then we have the expression, which is original dot clone. Okay, what? Takes one argument. Because we need to insert the result, which is evaluation dot expression dot clone. Okay, fair enough. So this was read end, and let's see read begin. So here, if self.solutions.get eval, let's solution else we show it like this, otherwise we are gonna show is equal to solution. Okay, and if we do eval 0 plus 1 again, we see it like 0 plus 1, and let's see, if we do end and we hit begin again, we are gonna see it like this being solved. So yeah, I mean, maybe we don't even want to show it anymore, I'm not sure. But yeah, you can solve it recursively. We apply 0 plus 1 is 0. Okay, yeah, like, doesn't really matter. We can show it, don't show it, I don't know. We can keep it, like, we can change our minds. It depends. Okay, so now that we have caching, basically caching should work. Like if we are trying to prove, I don't know, 1 plus 1 is equal to, but no, let's prove something else, like for all a in n, a times a squared is equal to a times a. Begin. We do next. Let's do it quickly. So power of 1. No. It's at the power of 1 is 1. And that should be it. So we proved it. So if we hit begin, we should already see it here. It's proven. That's cool. And what if we have something like eval 3 squared or something? But 3 squared is too hard. Let's do 2 squared. We can begin, hit next, and we have this formula which makes a big step. And at this point we can even say, okay, I want to prove something else. I want to prove for all a in n, 2 times a is equal to a plus a. I want to make this proof to make out my life easier, you know. So let's begin working on this theorem. Let's do next. And I think I want to do something like this first. And then we're gonna have this formula that we can apply, 1 times a plus a. Then we should have 1 times a is a. And then we should have this one. And then we can end. Right, that's pretty cool. And now if I hit show, because we are working with a stack, we are back at our initial expression, right? Because we ended this theorem, so we ended our intermission, let's call it, and we are back here. If I do next, we should have this formula available. 2 times a is a plus a. So we hit it, we get 2 plus 2. And at this point, you know, we can just prove it easily, like successor 1, then we use shift, then we another successor. I mean, it's fine, we can use that, but I wanted the successor 0 plus 3, shift, and then this one, and we get 4, and we do end, and you can see now that we got all of these steps. So 2 to the power of 2, we got that, we got this. So that's pretty cool, let's say. Okay. And, you know, at this point we can even try to if we do begin, and what's even cooler about this one is, let's say you are trying to create a theorem but you don't know the answer for it, right? Let's say you are a beginner in math or whatever, and you are trying to figure out how much is a plus b squared, right? You are doing this as an evaluation, but you know you need to make it right by giving the type of the variables. So we have a plus b squared, and we need to figure out the value of this thing. Okay. And what's cool about this interactive shell is that once you get the right value that you're satisfied with, you turn this thing into a theorem, which is kind of cool. So let's do begin. We are going to choose our evaluation and we hit next first. And as I said in the beginning, to solve this one without any caching, it took me 45 steps, right? Like without intermediate theorems that you can come up during evaluation. So here you can imagine that it takes like 10 steps to do a squared is equal to a times a for this one. So yeah, we just make it in one step because we cached this formula. So we just use that one. We get to this step instantly. Pretty easy, right? Pretty nice. And now we can do next again. And here we actually have some more formulas, like I guess this one is distributivity. I'm not sure how it's called. Like you have multiplication and then addition in parentheses, and you can multiply each term. I'm not sure. I think it's distributivity. Yeah. Okay, so we apply this one and we get something like this. Okay, that's decent. Next one that I want to apply is a times b is b times a. So I think this is symmetry or something. We apply it on the first term, and now we can distribute again the things. So apply this one again, and we get a times a plus a times b. All right. One thing that we have is a squared is a times a, but what if we want to prove the other way around as well? Because, you know, if it works one way, it should also work the other way. The thing that sucks is that we don't do it automatically. You have to prove it manually, which I think it's a good thing after all, because, oh, why not? But let's prove that for all a in n, a times a is equal to a squared. Okay, so we can begin this proof, and let's see how we can actually do it, because it's kind of annoying, honestly. Actually, we can just use this one on the right hand side. I didn't think about that. I wanted to do it in a weird way. I mean, this is the simple way. We can just prove it instantly, but I want to do it the hard way because I think it's cool to see what the hard way was before. So we apply this one, which is a to the power of a is equal to a to the power of 1, right? And we apply it on the first term, and then we have to apply it on the second term. No, not that one. This one. I want to apply it on the second term as well, right? And then we have a formula. Wait, we don't have it. Oh, it's because I'm using stdlib. aren't I? Yeah, I'm just using stdlib. Actually, I guess I'm just gonna redo this by using, and I'm gonna stop at this point. So where we left off, but I'm gonna use the other stdlib that I have because it's a bit better. So I'm just gonna make sure that I remember which ones we did. So a squared to a. Okay, perfect. So yeah, I'll catch you once I do these proofs again. Okay, so we are back at a times a is well, this one's not true, so we can just ignore it. So proof for all a in n, a times a is a squared. Okay, so let's begin. And I mean, if you have a false theorem, I'm not sure how you can maybe delete it. Maybe that's a good idea to add, like deleting things, but whatever. So let's see what we can do. So as I said, we do a to the power of 1, then another one here at the power of 1 again, and we should have I mean, I'm not sure why I don't have it in stdlib natural though, because I have something like this. Oh, it has parentheses. Okay, I forgot about parentheses. So let's add parentheses to the first item. And yeah, in this language, adding parentheses, it's like pretty important, because sometimes the order of operations doesn't matter, and parentheses show you how the AST looks like. So yeah, that's kind of rough. So a to the power of b plus c, and we get to this point, and let's say we want to, I don't know, evaluate 1 plus 1 separately, because we are cool and we can do that. So we can begin 1 plus 1. I mean, we did 1 plus 1 so many times. It's pretty funny. Okay, so we get that, and then we get the 2 basically. And it, we do next, we get 1 plus 1 is 2, look at that, and we can end the proof for a times a is a squared. And again, the simplest solution would be to use a squared on this item. So yeah. Okay, so if we hit begin, we don't have anything new except this one, which is false. But I mean, if it wasn't exists, then it should be true, because a is equal to 2, but we cannot do stuff like that. It's kind of hard. Anyway, so let's do for all a in n. I guess I have to evaluate it for all a in n, for all b in n. We are trying to do a plus b squared. Let's begin. So again, we just use this one, pretty easy. Now we were using this, we did this last time, and we open the parentheses again. So at this point we should have a times a is a squared, which we can use on the first item. Then we can do a times b is b times a again on this one. We can apply distributivity again, and we can apply a times a is a squared again on the b term here. Okay. Now at this point, what we want is to make here a times b and a times b, and we want to open the parentheses in such a way that we put these two things together, because right now this is the left hand side of the AST and this is the right hand side. So these two are pretty far apart. We need to get them closer. How we can do that? Well, with some combination of these two formulas. So here you can think about a plus b as this is a, this is b, and this entire term is c. So I think I want to apply this one first, so we get this combined with this, right? And then I want to use this one, this other one, to get this term. So this is now a from here, this is the b term from here, and this is the c term, right? So if we apply this one, we are going to combine these two together. So let's use this one, and I'm going to use it on this. All right, so now we have these two here. Now we don't have a plus a is 2a. Maybe we should add that. So let's evaluate. Actually, let's just do proof. For all a in n, we have a plus a is 2 times a. Begin. And here we are just going to use the simple one. Right? And we just end it. We proved it. So this would be how we can prove the other one, right? By using the formula that we have on the left, on the right hand side. So we just ended that. Okay, let's see where we are at. So we have this this stuff. So we can apply a plus a on that. A plus a is 2a. So we get this thing. Next thing is to remove some parentheses. We have too many. So let's first of all, let's remove that parenthesis, so the big one from here to here. And now I want to remove this this inner one. So parenthesis removal, this one, and we get to this, which I think it's a pretty good place to stop for this this formula. So if I hit end, we are gonna get the result, and you can see it's only 14 steps instead of what I got initially, which was 45. I mean, I'm not really keen on doing the 45 steps. It's kind of hard, but yeah. So we get even this one as a formula now. What kind of sucks though is if I'm trying to do 2 plus 2 squared. I'm going to begin it. Sure, we can apply this one, but it's still kind of hard to solve it because we don't have I mean, actually let's evaluate each one individually. So 2 to the power of 2. Let's do next. We don't have 2 times 2, so let's eval 2 times 2 because we are gonna need it anyways. So let's do next. Let's do it like this. And in the last session we had 2 plus 2, so maybe I mean we already had 2 plus 2, which was pretty funny. So let's begin 2 plus 2, and we have and now you can see that we have so many expressions in the stack. So once we finish one, it's gonna be like domino pieces falling, which is gonna be pretty cool. So 2 plus 2, we have to apply this logic with the successor and shifting. So let's do it a couple of times. We get to this point where we can do 0 plus, and then we are just gonna apply this stuff. So we got 2 plus 2, and we are solving 2 times 2 now, and we can hit next. We can use 2 plus 2. We can do end. Now we are solving 2 to the power of 2. We can use 2 times 2 here as well. We can end it, and now we are back here. So we got to this point. Let's use what we know, so 2 times 2 there as well. We also have this one, 2 times 2. I mean, at this point, we can even do something like this, which kind of sucks, but I'm just thinking maybe we have an easier solution from here, but I don't think so. I think we just need to go for addition and then just go for it with this one and just do the math. Okay, we also do successor 0, and then we are just gonna use shift until we finish it. Okay, 0 plus a. Now we can even, maybe we can just do that, I guess, a couple of times to get rid of the number from the starting position. Obviously we need to open the parentheses. But now I do have it, right? So I can just next it until we reach the end. Okay, nice. Curious why there are so many parentheses on this guy. Oh, I know why. It's because this was the second term. Yeah, I mean, it's fine. Doesn't really matter. So let's open the parentheses on that guy, and we can apply. We cannot apply that? Why can't we apply shifting here? We have successor of something plus something. So we basically have this one. Am I right? Uh, but why doesn't it work though? It's like we have this parenthesis. Like it should work on the arguments. Pretty weird. Let's backtrack. I feel like this is the good enough step. Let's add parentheses around these two, so around the last two items, and let's use this one, a plus b is equal to that. So now we have these two in a parentheses, we can apply some shifting on them. I mean, it was weird. Maybe there is like a bug in the solver where it cannot do some stuff with arguments, but I doubt that, to be honest. So we get to this thing, we can remove the parentheses. And there's parentheses on it, so let's remove those. We can even remove the parentheses on that and remove the parentheses on the 4. So now we can keep shifting from the first item to the second one. Yeah, such a repetitive process, but it's gonna be worth it. We are gonna get a big number. Okay, finally we get 4, so we need to, I mean, sure, we can make it a bit smaller. It's gonna be too big otherwise. We can remove successors from the I guess this is because I said that I don't want to do 45 steps, so I've got to do 45 steps. Okay. But you can see why maybe like automatic solver would have problems with things like this, because it's so many steps that it's hard to think that it's gonna make it like first try. So okay, let's almost there, and we got to 16, which is actually the result, and it's 58 steps. God damn. But yeah, we got to the result, 2 plus 2 squared. So now if we show this stuff, we see that we also have the results for these evaluations and for this one. As I said, this one doesn't work, but yeah, again, it's kind of annoying that we have to solve for each number, but it's fine, I guess. So yeah, kind of curious why that didn't work there, but again, don't really care that much. So yeah, I guess that's kind of how the language is supposed to be used, right? I guess it's more suitable for figuring out formulas like this one than computing with actual numbers, because the thing is, the language doesn't really know what plus does, we defined plus in here by saying stuff like 0 plus a is a, so plus is more of a, you know, pattern match. So if we find this pattern, we replace it with a. That's kind of a logic. And here as well with successor and b, if we find this pattern, we replace it with this pattern. All right, and then we have this one, we have these rules, and then we have some built-in rules that convert numbers into successors. And yeah, that's kind of how it works. So it's not really plus adds numbers. Plus is just a symbol in the language, and you know, it's defined here. It doesn't have like rules on literally adding two numbers. It's just, this is how plus works, you know, figure it out. Same for multiplication, same for powers. So again, it's kind of interesting that we manage to actually solve these things. So yeah, what about Fibonacci numbers? Like, we can copy paste this thing, what? Let's copy paste it line by line. Whatever, we don't need that anymore, so we can start again. So def fib 0 is 1, fib 1 is 1, and then we have this big one, but why doesn't it work? I mean, I'm not using anywhere this thing. Maybe it's because of copy pasting, so sadly I have to type it, right? That's all, yeah. Fib. Actually, what am I doing? It's like we already have the file, we can just load it. So examples 04 fib dash I. So now we can say something like evaluate fib 0, begin. We can next it. We already have the thing, so we can just end it, right? And what if we want to do eval fib 2, for instance? We can just begin this thing, and the idea is, so formula wants successor, so we have to apply successor twice. And we can apply this one. Right, I want to apply this one, and then we have fib 0, and we also have fib 1. And I mean, we already have 1 plus 1. In the last one we had 1 plus 1, now we don't. Yeah, let's do 1 plus 1 again. I mean, you can see how useful 1 plus 1 is, though. So, like, if you didn't know, 1 plus 1 is kind of useful. Okay, so we get 2 and show. Can next this thing, end it, and now we have Fibonacci number 2, and we can even go for 3. Oh, begin. Again, we need to apply this one twice, and then we can apply this thing. And now, since we have caching, we can apply fib1 and we can also apply fib2. Yeah. But at this point, we have to compute 1 plus 1 again, which is kind of annoying. I guess we use that one, and then 0 plus a, and then is that, and we end it. And then obviously you can even go further, like fib4, which is what our current solver is capable of doing, but that's kind of the max. So yeah, but I guess it makes it a bit easier to have that caching. So, but here you get to 2 plus 3, and it's yeah, maybe if we had some caching for simple additions, like built in, maybe define plus as something that's built in so that we don't have to do plus every time. But then again, it kind of takes like what's, you know, the main purpose of the language, which is symbols that don't have a specific meaning. They are just symbols. So instead of plus, you can literally have anything, and it does that operation that plus does. Okay, anyway, so we can just end it. Doesn't really matter. Right, we get 2 plus 3 as the result because we are too lazy to actually solve it, which is fine. Right, and yeah, this thing should still work even in non-interactive mode. I guess the interactive mode is, you know, completely different, or in a completely different file. It doesn't have anything to do with the solver. And yeah, I mean, the solver still uses the A star stuff, so oh, I guess if I use nature, maybe it's getting stuck somewhere. So I have to use stdlib for the simple. I like stdlib has less expressions. That's the idea. But yeah, anyway. So that was the one. Okay. I mean, it's decent. So I guess that's kind of all for today. So we managed to add this caching, which I think it's kind of useful, to be honest. It helps, at least in my testing, compared to what I was trying yesterday or the days before with the interactive mode. Caching really helps. And yeah, I guess that's kind of all for what I had in mind for Kroof. I mean, if we managed to prove something like a plus b squared, that's kind of enough for me, honestly. We even managed to use numbers for that expression and it worked. So that's kind of cool. Yeah, hopefully you found this series useful. We looked, even in the beginning, we looked a bit at C, like we tried to implement this thing in C, and once it got, kind of hard to work with the memory, we switched to Rust. And I think, even though someone would say, oh, C it's faster than Python. I mean, you cannot compare it with Python, but come on. It's like, yeah, but you also have to write good code. If you write trash code like I did in the beginning, just goofing around with the memory, it's kind of, maybe better to just use Python because you're not gonna waste time battling with the memory usage. And even though Python requires more memory and is slower, probably it's gonna use, you know, less memory and it's gonna be more efficient than if you write bad C code. So yeah, when someone says, you know, C is faster, it's faster if you are good at C. If you're not good at C, then you might as well just use Python or JavaScript, God forbid. But yeah, with you know, all that in mind, it was pretty cool project to try. So I mean, if you have any other ideas, maybe we can add certain features in the future. So who knows? But I think for me, or at least for now, it's kind of done. I think we have all the features that we were trying to get, like having functions, types, operators, and then all of that pattern matching, solving expressions, proving things. That's, you know, that's even cooler. We haven't fully gotten into the for all and exists stuff, into the quantifiers, but yeah, I mean, I think it's fine. You know, that would be cool to be able to have things like I don't know, like evaluate 1 plus a is equal to 0 and then, you know, give me the value of a. That would be cool, but you know, it's kind of out of the scope in my opinion. Like if you want to do 1 plus a is equal to 0, you would have to do it manually first, figure out that a is equal to 0 minus 1, right? Like do the things yourself and then you have to evaluate 0 minus 1. You know, it's kind of janky, but yeah, I feel like the proof got to the objective, to the final objective. So yeah, if you want to see any other features, I mean, as I said here, like being able to have lists, maybe tuples, that's crazy. Stuff like lazy evaluations, maybe a debugger, but I guess debugger we already did, being the interactive mode. And yeah, maybe bigger stdlib, but that's a matter of time, right? But yeah, I guess, you know, this one we did is the interactive mode, but yeah, having more complex types, more number types and stuff like that could be worth to look into that in the future. So yeah, hopefully you enjoyed, and let's see in the next one. So until then, see you.